we are discussing the addressing modes of an instruction. To recall, the addressing mode specifies the way the operands are addressed in an instruction. We discussed 4 addressing modes: register addressing mode, direct addressing mode, immediate addressing mode, and indirect addressing mode. We started the discussion on register indirect addressing mode. Let us continue with the discussion. Let's take this example that move this is a registered indirect addressing. This means that R2 is containing the address of the operand. Okay, for example, that if this is R2 and say it is containing 600, okay, then say this is a memory and say this is 600 location, then the content of this 600, say this is 190, is the operand. Therefore, the effective address here is the effective address of source is equal to the content of R2, and this is direct addressing. Therefore, the effect of this instruction will be take the content of R2 and then move it as content of X. Okay, this is register indirect addressing. We have already discussed it in the previous lecture. Now, what can be done here is this, that this register indirect addressing, the register specified, can be pre-incremented or post-decremented. Okay, for example, if we say that plus R2, then it means that increment the content of the register R2 first by specified amount, say 2, and then take its content as the address of the operand. Okay, the effect of this here will be, say, if I say that move X this, then say this is 600, say R2 was containing 600, and this instruction has been executed, then R2 will be first incremented to say 602, okay, then its content will be taken, right? Similarly, we can say that move R2 minus to say X2, which means the register will be decremented first and then this its content of the memory location pointed to by R2 will be taken, right? Now you see that this is more or less equivalent to that can be used for the push and pop operation that we had with the stack pointer. Okay, for example, if we say that move say X2 plus R2, that's equivalent to our push X operation. Similarly, if we say that move R2 minus to Y, that is equivalent to say pop Y instruction. Here we are using stack pointer, the system is using the stack pointer, and here the user is specifying R2 as if as a stack pointer. Therefore, with this addressing mode, the user can have as many stacks as he wishes to define in his program and can use the registers, okay, any of the registers like say R2, R1, etc. Okay. Now, this is what is the register indirect addressing. Let's come to what we call that displacement addressing. Okay. In the case of a displacement addressing, what happens is that with respect to some base, okay, displacement is specified, and the displacement has to be added to get that effective address. Okay, it can take various forms. Three very important forms are available and almost are used in all the computers. First one of them, say, is indexing. Okay, and sometimes we call that indexed addressing. In the case of an indexed addressing, what happens pictorially, it is like this. Okay, let's say this is the instruction. In the instruction, you specify two things. One is an address X, another is a register R2, we call an index register. Okay. An example can be like this. Say, if we say that move X R2 to say some register, say R5, here in fact what we are specifying is an indexed addressing, right? What it does is that X is a memory location, say here. It takes the content of R2, adds X with it, right? And then gets the effective address. Therefore, it is essentially from X as if a displacement, okay, say this is a displacement that is contained in R2 is added to get the effective address from where the content is taken, right? Now, for example, the effect of this instruction will be that take X, add the content of R2, get the effective address, takes its content and send this as a content of R5, which is a destination over to here, right? Now, this indexing can be very fruitfully utilized when you are accessing sequential memory locations or say memory locations, right, which are memory locations that you want to access one after the other, right, in terms of its displacement. Right. Let's take an example. Say you take a high-level language program statement, a for statement in C. Okay, a double address assembly language code may look somewhat like this. Okay, it says that for I equal to 0, I less than n, I plus plus, that means increment I, take the content of AI, take the content of BI, add them and store as a content of DI. Okay, the assembly language form will be somewhat like this. Okay, for example, let us take R5 as that index register. We'll clear R5 first, then add AR5 with BR5. That means take the content of A displaced with R5, okay, then take the content of B displaced with the content of R5, okay, right, take their content, add them, okay, and store them in BR5, right, then add 2 to R5 so that you can go to the next memory location. Say, for example, say this is B, okay, this is the first location of B, then this is the second location of B. I am assuming that these locations one after the other are 2 bytes apart. That means one data is taking 2 bytes. Therefore, you see I am adding 2 to R5, then comparing whether I have crossed the limit or not. Okay, comparing n with R5, if we find that the result is positive, jump on positive, I am coming back to the loop to do this operation once more, right? Here you see that indexed addressing is very helpful in such cases where I am trying to take the contents sequentially. Now that I can be incremented by any value, therefore if you are going to take at regular intervals okay, the content of memory locations, then indexing is very fruitfully utilized, right? Now let us take the case, the same case with a single address machine, okay? In the case of a single address machine, once more, say all the addresses are only single operand, okay, except the where both the operands are registered, where we have used two registers, okay, and that is permitted. We assume that that is permitted, right? Now here, once more, we clear R5 first, then load accumulator BR5, that means index addressing we do, add AR5, here also we do an index addressing, then store accumulator, the result, into BR5. Then to check this one, we move the content of R5 to accumulator, add 2 to it to make it I++, right? Then move the content of accumulator to R5, then check the limit, that compare the accumulator with n, because the result is still with the accumulator, and jump on positive to loop. We go on doing this loop. I have given this example to emphasize two things also. You see that in the case of a double address computer, the code is somewhat smaller, okay, than in the case of a single address computer, where the code is somewhat lengthier, okay, but we can do the job in any way, and the addressing mode is valid, okay. Let me remind you once more that what we are doing here, that we have taken two, so to say, two hypothetical computers, okay. One is a single address one and is a double address one, right? This is index addressing. Let us now come what we call is under the displacement addressing, base register addressing. Here what is done is this, that a base register is specified, and in the instruction the displacement is here, okay. For example, the content of the base register is taken, then the displacement comes from the instruction, these two are added, and we get an effective address, okay. Now let's see, for example, this can be useful. Say this is a data area, right, in a program. What we can do is this, that base address of that data area, which is a 1000, can be loaded in the base register, and displacement in terms of the base register, say, can be specified in that instruction itself to come to the particular location. Therefore, here the effective address is the content of base register, add with the displacement, and then you get that effective address, and its content can be taken for as an operand. Okay, this is our base addressing, right? And third one that we can discuss, we'll discuss is PC relative addressing, okay. Here the displacement is specified in terms of, okay, the program counter itself, okay. Let us take an example. Say here the program counter is here, that instruction contains a displacement which is taken, content of the program counter is taken, these two are added to get the effective address, okay. This is the effective address, okay. Let's take an example. Say move x to R5, we took this to be a direct addressing, x is a direct addressing, okay. Now what we can do, let's see that when this particular instruction being executed, the program counter will be pointing to the next instruction, okay, which is at location say 0704, if we assume that this instruction is at the location 0700, right? Now instead of keeping x in this instruction, what we can do is this: we take the absolute location of x, okay, subtract the content of program counter from x, okay. Let's see, the content of program counter is 0704, say the memory location for x is 0904, then the displacement we get is 200, okay. Then instead of keeping the direct address here, we can keep instead the displacement y, which is 200 here. Now when actually computing the address of that instruction, address of the operand, the source operand, we take the program counter which is 0700, add the displacement which is say 200, right? And in that case we'll get 0904, which is the address of that operand, and we can take the operand from here, okay. Now this is displacement with respect to the program counter, and therefore we call it a PC relative addressing. Now the advantage of this PC relative addressing over direct addressing is this. Say for example, if you sometimes in the case of a multi-programming environment, if you want to shift this program somewhere else, right, then the absolute address of x, which is 0904 now, will change, okay, and therefore you'll have to make a change here if you want that the program runs correctly. But if you make a PC relative addressing, then the displacement, that means the relative address of this x with respect to the program counter, will remain unchanged even if you shift the program to somewhere else, and therefore you don't have to make any changes in the direct addresses that you use over here. And that is why that PC relative addressing is okay, gives a position independent code. By that it's meant that even if the program is shifted from one portion of the memory to another portion of the memory, the values of the addresses need not be changed, okay. Now we see that in the case of a displacement addressing, therefore, we have discussed three very useful addressing modes. One is that indexing, one is the base register addressing, and one is the PC relative addressing, which can be used, okay. Now let me tell two things, that say the addressing modes that we have discussed so far, like say single address, double address, and sometimes we talked about triple address. We have not given any examples of triple address machines, triple address instructions here, okay. We have talked about such assembly language codes, okay, such symbolic mnemonic representation of the programs, okay. Now let me emphasize here that the particular assembly language symbolic mnemonic that I have used, okay, are so to say of hypothetical machine, right, of two errors, okay, though it's very closely resembling to one of the very popular machines like say PDP-11 in the case of a double address instructions. But one important thing is that though I saying that these are all in terms of a hypothetical machine, the instructions themselves that I have talked of and the addressing modes that I have talked of are very real. Okay, the actual form, the way that assembly language is written or it is implemented in instructions may change, okay, and may vary from machine to machine, but the addressing modes are very much applicable, okay, to more or less every machines that nowadays in operation, okay. Similarly, the single addressing modes that we have talked of here, right, also so to say of a hypothetical computer, right, but one thing is that the addressing modes is still very valid and the instruction set that we have talked of is very valid, right. Now the thing is that these addressing modes as well as the instruction set, okay, the number of instructions that are included in the instruction set, okay, is gradually increasing or gradually increased, okay, as the semiconductor technology, okay, VLSI technology advanced, right? More active elements could be incorporated into the VLSI chip, and therefore more and more instructions were incorporated in the computer. More and more addressing modes were also incorporated in the computer, right? And whatever we are discussing in terms of what we call a CISC, or complex instructions set architecture, okay? Complex instruction set architecture or complex instruction set computer, CISC, complex instruction set computer. Okay, now here essentially the uh, idea is to incorporate very powerful instructions, okay, so that the machines can be almost, I should say, pushed up to the level of high level language it is supposed to ultimately, okay, that execute, right? I mean, execute in the sense that it will be converted into, in any case, the machine language and will be executed. But if the instructions are very close to the high level language machine, okay, high level language, then it's expected that the machines will execute this high level language quite faster, okay? For example, one such example can be that of a, say, the Pentium machine. Let us see that what are the addressing modes the Pentium machines are having, okay? Now, see, this is the Pentium addressing mode. Here you see that it has an index register, okay? Here there is a base register, there is a scale register, okay, which can give either 1, 2, 4 or 8, okay. This is instruction, say one instruction that is being executed, right? Then effective address is generated, can be generated, that you take the content of index register, multiply with any of the scale factors over here, what you get, okay, that you add with the base register to get an effective address. Now, the displacement from the instruction, that also can be added, okay, to get that effective address. Now, once you get that effective address, that is now added with segment register, the content of a segment register, and a linear address is obtained here. Okay. Now, you see that though in the case of a, I mean, we have somewhat simplified the segment register portion here. In fact, in the case of a Pentium, there can be corresponding to a program, okay, program module, that can be 6 segments, and the segment register in fact points to a segment descriptor. The 6 segments are that code segment, data segment, then extra segment, and so on. The segment registers in fact point to a segment descriptor which contains the access rights and the limits of the segments, okay. This portion I have simplified somewhat, okay, because we'll be discussing some of these things in the, when we'll be talking about that memory management later on. Now, the content of the segment register is then added with that effective address to get the linear address, okay. The purpose of the segment register is somewhat this. So, for example, say right, this is the segment, okay. Now, what is done is that segment register corresponding to the segment point to the beginning of the segment. Now, if you want to move the segment from these portions of the memory to somewhere else, okay, say for example, if you want to move this segment to from here to somewhere else in the memory, say here, then what you have to do is you have to change the content of the segment register only, and now that entire addressing that was applicable here will be applicable here. Okay, that is the, I should say, that importance of a keeping a segment register to point to the beginning of the segment. Okay, now when you have given this diagram, the different addressing modes that are available are this, okay, that we can have an immediate addressing where A is operand, where A is specified in the program itself, right? Sorry, A is specified in the instruction itself, right? Then register addressing, we can have the linear address, it's a register itself. Displacement addressing that we have talked of, the content of that segment register plus the displacement, okay, content of segment register is added to the displacement to get the linear address. The base addressing is that you take the content of base register, add the content of the segment register to get the linear address, okay. Then that base with displacement is that you take the content of base register, take the displacement from the instruction, add the content of segment register to get the linear address, okay. Similarly, that scaled index with displacement is that you take the content of the index register, multiply with the scale, okay, add the displacement from the instruction, add the content of a segment register, you get the linear address, okay. That means you take the index register, you see, if we take this one, right, okay, take the content of an index register, multiply with the scale, the value the scale register provides, okay, add the displacement from the instruction, okay, and then add the segment register content to get the linear address, okay. Similarly, base with index and displacement is take the content of segment register, take the content of base register, then take the content of that index register and take the displacement, add all of them together to get the linear address, okay. Similarly, base with scaled index and displacement is that take the content of segment register, content of base register, content of index register multiplied by the scale register, content of scale register, okay, and add the displacement to get the linear address. And the relative address is simple, you take the content of program counter and add the displacement with it, okay. What I suggest is that you take this diagram, okay, take these addressing modes, okay, right, and then see that how the linear address can be computed from the arrangement that has been shown over here, okay. Now, here L is the linear address, X has been taken as a content of X, R is a register, SR stands for segment register, I stands for index register, B for base register, A for content of an address field in the instruction. That means whatever I am talking about A here is essentially the content of the address field. Say this is A, right? And so to say that taken as a displacement, okay. Now, I mean, when I say that it's taken as a displacement, it may be other way around also, that this is the address and say, for example, say this is the address, this is taken as a displacement, okay. Therefore, what is important is that this A comes from the instruction, okay. A comes from that instruction. Now, you take this as an explanation of that what are the different symbols that has been used here, okay, and you take this one, okay, to see from this diagram how the address is being computed, okay, and this will be self-explanatory as such, okay. Now, one important thing is this, that when we are talking about instructions and addressing modes, okay, now as I told earlier in the previous lecture, that sometimes we talk about that orthogonal instruction set. In the case of an orthogonal instruction set, we mean that the way that you specify the addressing mode is dissociated from, so to say, the opcode, okay, or the instruction part of it. That means any instruction, add, subtract, multiply, divide, or say, for example, move, transfer, jump, these instructions specifies what to be done, and the addressing mode specifies that from where the operand has to be taken or where the operand address has to be taken, okay. And any operation can be associated with any addressing mode, okay. Such a thing is called so to say that that orthogonal instruction set, right? The example that we have given earlier, right, say this one, the assembly language code for a double address, the assembly language code for a single address, okay, where we have specified, you see, the instructions here and the address of the operands here. These two, if we can dissociate, and anyone can be used with anyone, in that case we call an orthogonal instruction set. And in such cases, a possible instruction format can be like this. For example, you keep that opcode, right? You keep that mode of the destination here, right? 3-bit can say talk about 8 modes. You talk about the register that is associated for the destination. You talk about the mode that is associated with the source here, and you talk about the register that is associated with the source here, okay. That can be a 16-bit format. Possibly you can just expand in the case of a 32-bit machine. Destination memory address you specify in the next word, and the source memory address you specify in the next word of this instruction word, okay. Now, as I was talking of, right, the single address instructions that I was talking of are very close to that some of the microprocessors, very initial stage microprocessors, okay, that were available in the late 70s, okay. The double address machine, the instructions that you're talking about, okay, are more or less similar to that PDF11 and VAX11 machine, okay, that were in that available late 70s till mid 80s, and the instruction format that I talked about, like Pentiums, are very much available nowadays, okay. And all these examples, I mean, apart from the single address one, all these examples are, so to say, belongs to CISC, or complex instruction set machines, right? But from 80s, okay, there is a different line of thinking that started, and it says that not to complicate the instruction set too much, okay. Better you use a very simple instruction set, a simple addressing mode, okay, and let us analyze what can be the advantage that we can get out of it, okay. This line of thought is called RISC, okay, or reduced instruction set computer. Here what we do is that we take a limited and simple instruction set and addressing mode. The advantage here is this, that the hardware that is needed to decode an instruction and execute an instruction is much simpler, and therefore it takes much less space in the VLSI chip. Therefore, much more space is available for other purposes. This is one advantage. Second advantage can be that since the circuitry is simple for decoding as well as execution, the time to execute an instructions, to fetch and execute instructions will reduce, okay, and therefore that instruction execution will be faster, right? And as the chip area, more chip area is available, you can have a large number of general purpose registers, okay? If you have more general purpose registers, then you can keep many operands within the CPU itself, and therefore to get an operand, you don't have to go to the memory to fetch the operand, and any memory access is time consuming, and therefore if you can keep more operands within the CPU itself, your program execution speed increases, okay? Now, since more on-chip cache also you can incorporate. By cache we mean a memory which is within the CPU and so to say acts intermediary between the main memory and the CPU. That means a portion of the program or the data can be prefetched and kept in the cache, and the CPU need not have to go every time to the main memory to get either instructions or data. Now, if you have more on-chip cache, in that case, you can execute an instruction much faster, okay? And another is that the reduced instruction set computer tries to do is that optimize the instruction pipelining. As we indicated earlier, that when you are executing one instruction, okay, the other instruction can be fetched and can be prepared for execution. By that I mean that more than one instructions can be at different phases of execution, okay, simultaneously or concurrently, and this is called pipelining, right? Now, that optimizing that instruction pipelining is a feature of the reduced instruction set computer, which also increases the speed of execution of a computer. Now, with this, okay, many of these systems have come to the market. They are very powerful, okay, and the basis of, say, bringing in reduced instruction set with these features are one of the important characteristic is this, that though you can have a very complex instruction set and very powerful instructions, right? But your high level language program have to be converted into machine language automatically by means of a compiler, and many times the compilers cannot exactly fit that complex instruction to a high level language construct. As such, it has been found that not all complex instructions are utilized, okay, in that machine language program corresponding to the high level language program. Many times what happens is that a subset of the complex instruction set is being utilized. So if that be the situation, then why not try to have a reduced instruction set computer where the instructions are of limited size, okay, and simple, okay, and the addressing modes are also simple, so that these instructions can be used with the benefits that I have already stipulated, right? And with this end in view, many reduced instruction set computers have come into the market. They are very fast and very powerful and work as servers, so to say. One addressing modes of such a reduced instruction set computer called the Power PC has been shown here. Okay, you see here I've shown the mode in green and the address computation algorithm in black. These are the addressing modes simply that are available. This is indirect, that means you take the base register content, add a displacement, right, to get an effective address. Indirect ingress, which means that you take the content of a base register, add the content of an index register, and then get an effective address, okay. For the branch addressing, you can have either an absolute addressing where I is an immediate value, okay, that means the address that you get from the instruction itself. It can be PC relative, okay, or it can be indirect in terms of a register, we call it link or count register, okay. For addressing the operands, say fixed point operands, the fixed point addressing we have that general purpose registers is that effective address. We specify a general purpose register, okay, as an effective as an address of that operand, or we can have immediate operand here where that uh, where that where that a portion of that instruction contains operand itself, right? Similarly, for the floating point computation, we have floating point register, which is the effective address. That means the operand is in the floating point register itself. Now you see, it's a very simple set of addressing modes. If you have to do any fixed point or floating point operation, basically you will have to bring the operand to a general purpose register or a FPR by means of the load store addressing, right? Now what I suggest is that you see these addressing modes in terms of the symbols that I have used, which has been explained here. Okay. Now this is an example of a RISC machine, right? RISC computer. I have shown it as, so to say, as an example of a simple RISC architecture. Now, one important aspect of a central processing unit is registers. Okay. Now, as we have seen in our instructions, we have very frequently used registers. Okay, either as a source or as a destination. As I said, that if you have more registers within the CPU, then you can keep more operands in the CPU, and therefore your instruction execution time will reduce. Okay. Now, the registers are classified in more, so to say, into two broad categories. One is a user visible register, another is user invisible register. For example, the general purpose registers that we talked of quite frequently earlier. We say that a register is a general purpose one if we find, or if we can use this register either for address, keeping an address, or for addressing, or keeping a data. Okay, and we call this as general purpose register. Then we can have data registers, we can have address registers. As address registers, we have said that we can have a base register is an address register, index register, segment register, stack pointers are all address registers. We have condition codes registers also. Mainly they are flags, and sometimes they are 1-bit registers, so to say. And while we're discussing that arithmetic operations, we talked about the sign flag, carry flag, overflow flag, parity flag. There can be one flag or one bit registers interrupt enable, saying that the interrupt from outside is enabled. By that we mean the CPU can be interrupted, and sometimes the CPU can be in the supervisor mode or the user mode. That means in the case of supervisor mode, the CPU can execute some privileged instructions. We'll have occasions to see that what privileged instructions are when we'll be discussing that operating system, right? There can be one register, 1 bit, okay, or more than 1 bit if needed, that which tells that whether you are in the supervisor mode or in the user mode. User invisible registers are program counter, okay, that instruction register where the instruction is kept before decoding, memory address register, memory buffer registers, like this. Okay, they are sometimes called the control and status registers also. Now, in many machines, the program counter is visible also. Okay, therefore, sometimes we say that program counter is partially visible. That means it may be visible, it may not be visible. Okay, and one aspect of that total registers is this, that as I said earlier, that if you have in any case that more registers, the better for execution of the instruction. And that is all so far as your that instruction set and addressing modes are concerned.